All right, so let's just talk about a few questions from 1.1. You guys say you have no problems with it. Let's just make sure we're all on the same page. So question number one, when you start, question number one, we're talking about, what's reasonable, what assumptions were made, trying to think about logic and reasons for things, right? So question number one says, Troy works in a ski shop in Whistler, BC, where 3 types of downhill skis are available: parabolic, twin tip, and powder. The manager of the store has ordered 100 pairs of each type in various lengths for the upcoming ski season. Okay? What conjecture did the manager make? Explain. Okay, so what conclusion, upon ordering there, before he ordered, what conclusion or what assumptions was he making? What idea did he have that was going to happen? So give me your answer from number one, someone. Yeah.
All types of skiing is like the same levels of popularity.
Okay, so the popularity of the 3 different types would be roughly the same because he ordered 100 pairs of each, right? Awesome. So if there were 3 types and he only ordered 1 type of ski, then the idea is based on whatever previous data, previous experience, or his knowledge of the ski hill itself or whatever, then he would be assuming that no one would want these 2 types, but they would only want this one. But because he ordered 100 pairs of each, he's assuming that they'll all be equally popular. Okay, good. Anything else that you guys wrote down that you want to check on, or did you write anything different than that for number one? Okay, you could have maybe said something about the number, 100 pairs of each type. The manager thinks he's going to sell, around 100 pairs of each type. Why didn't he order 10 of each, right? If they were equally popular, he could have ordered 10 of each. But why do you order 100? Okay, well, maybe in past he's sold roughly 100 pairs of each, and so that's why. So you might have commented on the number of each. Okay, so let's take a look at number 2. Thomas gathered the following evidence and noticed there's a pattern. 17 times 11 is 187. 47 times 11, 451. 23 times 11, 253, and so on. 62 times 11, 682. So you see that the first and last digits are highlighted, right? And they happen to correspond with the numbers that are multiplied by 11, right? So 11 times 17 has a 1 as the first digit and a 7 as the last digit. Thomas made this conjecture. When you multiply a 2-digit number by 11, the first and last digits of the product, that is the result of multiplication, are the digits of the original number. Is Thomas's conjecture reasonable? Develop evidence to test this conjecture. So when you develop evidence to test, that is, you're basically doing examples and seeing if they check, if they work with the conjecture, or if they don't work. So that's what you're doing. Okay, so when you multiply a 2-digit number by 11, the first and last digits are the number of that number. So did you guys find some more examples that checked off with this? Did you find any examples that did not work? Some feedback. Yes?
66 times 11 is 726.
Oh, okay. So you found 66 times 11 was 726. So 66 times 11 has a 7 and a 6 on either end. So that one doesn't work. Okay. Were there others that did work that you tried?
11.
Or 11 and 11? 121. Okay, good. Yeah. Okay, so we found one that didn't work. Okay. Anything else that doesn't work? Did anybody find? Yeah?
Well, we have like a not formula, but like a rule for it. If the digits of the number add up to a double-digit number, it won't work.
Oh, okay, okay.
66 adds up to 12. So that's
okay, very good. So you went a little bit further and noticed a pattern in what doesn't work. So if the digits, if the sum of the digits of the number, like the 1 and 7, if they add up to another single-digit number, then you say this pattern works.
Yeah.
But if it's greater, okay, well, we could pretty easily test some of that too. I like that. And that's a great pattern that you've recognized. So 66 would add up to 12, so that's why it wouldn't work, according to your idea. Awesome. Let's check. Okay, so let's check like 54. Let's check that one. So 54, 5 and 4 add up to 9. And look at that, 5, 9, 4. So that works. What about 56? And that would be one that adds up to a 2-digit number, and that doesn't work. Okay, all right. So did anybody else notice that, or is anybody... Okay, did anybody find any problems with that rule? No? Okay. So here's the idea. The idea is that you test conjectures to see if they're reasonable or not. And maybe a conjecture or an idea works for most circumstances, but just not all the ones that you can think of. So again, we are getting into the area where what's reasonable, what is reliable, what is a rule that works for every single situation, what is not a rule. So as we move through this chapter, we're going to be proving things. So if there's a rule, we're going to try and prove it that is a rule all the time, and that's the goal. But right now, we're just kind of testing ideas. Okay, so make a conjecture about the sum of two even integers. Develop evidence to test your conjecture. So basically what you're asked to do here is to test what is the sum of two even integers. Observe what that sum, that's when you add, observe what that sum looks like in all those cases and see if you can come up with a rule. Okay? So if we do, and I'll just do this on the calculator so we have a record. So we're adding even integers. Okay, so 2 plus 8. Okay, those are two even. The sum is 10. 4 plus 16. The answer is 20. One more, 8 plus 22. Those are both even. We get 30. So, oh, that's interesting. 10, 20, and 30. I don't think that's, let's do one more. 8 plus 4, they don't all end in 0, but okay, so 12. So what do we notice about all of these sums? What did you guys write down? Yeah.
Even integer plus an even integer is equal to an even integer.
Okay, so when you add two even integers, the sum is also even? Okay, anybody else get that?
Yeah.
Okay, all right, so if you were able to test this and you found that the sum of two even integers was not an even integer, then that might be a conjecture that's unreasonable, right? Because you found an example that doesn't fit. But that is probably a pretty good rule. And again, we will be looking at proving that algebraically in upcoming sections. But right now, we're just looking at a bunch of examples and gathering patterns. So, okay, that's great. So you guys, you might say that the sum of two even integers is an even integer itself. And integers are negative numbers too. So I guess we should have tried like -2 plus -8. Okay, that's a -10, so that's an even integer. It's negative, but that's an even number. So integers are positive and negative whole numbers, right? That's what integers are. Okay, all right, I won't do all of these for you, but were there any other questions from this assignment that you had trouble with or want to ask me about? Yeah?
Is there a thing like a seven-sided shape?
Is there a thing like a seven-sided shape? Yeah, there is. You can have a seven-sided shape, yeah. So there's two names that are reasonable for that. They're acceptable. Septagon and heptagon. Heptagon and septagon. Both of them because yeah, both of them are acceptable. Yeah. That's right. Hexagon is 6, septa or hepta is 7, octa is 8, nona is 9. Deca is 10. Dodeca, I think, is 12. Anyways, I had a poster once with all those names. I took it down. Okay? All right. Anybody else, any questions about the assignment, which is, where is it, right here again? So 1 to 6, 9 to 11, and 16. That's your assignment for 1.1. Okay?